I'll make sure that you have the other slides of the problems that we worked through there. All right, so rounding out the things that we need to know how to do the derivatives of, e to the x, and in general, any exponential function with any base, we need to be able to do the derivatives of those, and the logarithms, natural log and log of any particular base, and we'll discover why calculus tends to favor the natural log and e to the power over the other ones. And then a power rule for arbitrary real powers. Okay, that's going to introduce us to some functions that we're frankly unfamiliar with. I can say we because you guys are unfamiliar with them. All right. And obviously we want to be able to do this because we know so much that has to do with growth, and all of that is modeled with exponential functions. So being able to understand them better, which is what calculus does for us, is important. So one approach to doing this, taking you back to things that you've done in Algebra 2 and in pre-calculus, is whether or not you remember the change of base formula. And I never totally remembered the change of base formula, but I remembered a process, and I'm going to demonstrate that process. Okay, so if I want to write this as something that uses e as a base, I'm going to give it a name. Okay, my name for 2 to the x is going to be y. Okay, and now I'm going to solve for x. The way that I solve an exponential function, when I have that variable in the numerator, the tool is logarithms, right? And I can choose any logarithm that I want. I'm going to choose natural log in this case. And if I apply a natural log to both sides, I'm going to get x times the natural log of 2 is equal to the natural log of y, right? And so now, how do I get rid of a natural log? If I wanted to solve this again so that it said y again, okay, I get rid of a natural log with an e to the power. So if I did e to the power here on both sides, then e to the natural log y is just y, and this becomes e to the natural log 2 times x. And I just rewrote this with a base of e instead of a base of 2. And I could show that this was equivalent. If I'm looking at e to the natural log 2 times x, the x is not inside that natural log, right? The fact that these are multiplied together means that I could rewrite this as e to the natural log 2 all to the x. My power to a power rule says you multiply the powers, but e to the natural log 2 is just 2, so this is the same thing as 2 to the x. So I can change the base of that exponent into anything that I want by the choice of logarithm that I use to solve for x on the first step. So we'll talk about why this is important as we go along here. A reminder again here of how to solve logarithmic or exponential equations. And the important first step here is that you can't apply the logarithm until you've exposed the base. Okay, so the first step in this process has to be to get rid of this 12. Okay, if you don't get rid of the 12 first, this is 8/3 is equal to e to the 0.07t. If you tried to just hit this in the beginning with a natural log 32 equals natural log of 12 times e to the 0.07t, you can do that, and people tend to go that direction, but then they forget that this is a natural log of a product. So this becomes natural log of 12 plus 0.07t equals the natural log of 32. And then they have to subtract this over there before they solve for the t. Okay? On here, we've now exposed the base, so we can do a natural log on both sides. And natural log is the choice here because the base was e, and they mesh together perfectly and cancel each other out. So I would get a natural log of 8/3 is 0.07 times t, and so t is just whatever the natural log of 8/3 is, and I divide by 0.07, whatever my calculator tells me that number is, although I am fine with an answer like that most of the time. Okay. Just because then I don't have to go and potentially make a mistake punching something into my calculator. This is an exact answer. The other thing when I go to my calculator is I'm only going to get an approximate answer. So this is probably a better way to leave that. It's not necessarily super informative in terms of numbers, but it is an exact answer. Okay. Inderivative, remember, was the numerical derivative calculating feature of your graphing calculator. And we have the dy dx that we can type into Desmos to do that. So a word of warning before we go here. These are very different things. X to the a, this is a power function. Right? But this, a to the x, this is an exponential. And the first thing that we're going to learn here is we know what our power functions look like, and exponential functions don't really look like the power functions. Okay, they don't behave the same way. And so what we can't do if we're trying to do the derivative of the e to the x, this is not equal to x times e to the x minus 1. Okay? That just does not work. Okay? For one thing, our exponential functions we know have graphs that look like this. And so what can we say about the slope of the tangent lines on a graph that looks like that? Tangent lines should always be positive. Well, x times e to the x, that opens that x up to give me a possibility of something that is negative. And I don't have any negative tangent line slopes on here. I can also see if I was looking back here, if I was just trying to sketch the graph of what this might look like, well, these tangent lines back here are almost flat. They're very close to 0. So these points out here, I'm getting points that are very close to 0 out here. Okay. Then it turns, and out here I should get numbers that are bigger and bigger, very getting to be infinitely large as they go along there. Okay. So for negative values of x, I should get things that are close to 0, and certainly putting a number like negative infinity in there doesn't feel like that's going to get me very close to 0 or make it positive along the way. Okay. It would do okay on the infinity side, it looks like there, but lots of evidence to say that this is not going to work, so I'm going to erase it because it's wrong, and I don't like spending time looking at wrong things. Okay. So if you have a calculator open, let's go ahead and graph e to the x. And I'm going to attempt to share a screen from a different machine here. So I'm going to stop sharing that screen, and I'm going to start sharing this screen. Okay. So that is what e to the x looks like. Most people don't have a real sense of just how fast exponential functions grow when they start to grow. Okay, it is crazy, insane fast, and I think we did talk about that when we were doing some of the review stuff at the beginning here. Okay, so The next thing I want you to graph is the derivative of that. So we'll use the ddx feature of Desmos, and I'll graph ddx of e to the x, and what do I see? Well, it says it's going to be in blue, and I see the blue function there, but I don't see the red function anymore. Did it delete the red function? If I play with that, I don't see the red function showing up anywhere, unless, oh, if I turn the blue one off, then I can see the red one. Which means what?
They're the same.
They are the same function. The derivative of e to the x is e to the x. So let me jump back over to here. So our conclusion, I guess I am recording. Okay, I don't know what all showed up there. Okay. But the derivative of e to the x is e to the x. This function is its own derivative. Kind of feels weird that we waited until the very end of this chapter to find what is apparently the easiest possible derivative to do. Okay. So that means that if we have an x and we do e to the power on there, that's how we would represent the exponential functions, is base to an empty set of parentheses. The derivative of that is just e to the power. Okay. And whatever is at the beginning of the arrow gets loaded in there. So this is our general arrow diagram for derivative of e to the x. That now is eligible to be a part of everything else that we do. Okay, we can put anything in the power of the e now as we go along and would be able to take the derivative of that. Okay. Chain rule, product rule, quotient rule in combination with any of the other functions that we know how to take derivatives of, which is everything now except for logarithmic functions and exponential functions that might have a different base. So, for example, we start here with a t, that's a polynomial, so 2 empty set of parentheses cubed minus 6 empty set of parentheses plus 1, and I can do that because I know the derivative will be 6 squared minus 6, and t loads into that. And then this goes into the power of e, and the derivative of that is e to the power, and what came out the end here was a 2t cubed minus 6t plus 1. So that loads in here, 2t cubed minus 6t plus 1. And so my derivative is 6t squared minus 6 times e to the 2t cubed minus 6t plus 1. What we're going to find is the derivative of an exponential function will always have that same exponential function in the problem somewhere. Okay? It always shows back up again. That's the kind of what happens because of the shape of the exponential function, where it's really the function itself is close to 0 way out to the left, and its slope is close to 0. As we move to the right, the slope gets steeper and steeper, and the values also get steeper and steeper. So the nature of the input-output relationship is so similar to the nature of the tangent lines. All right? So if we want g prime of x here, we've got the x goes into a sine first and gives us a sine x. And then we put that in the exponent of 2, and then we multiply by 10, and we're about to figure out that we can't quite do this one yet. Derivative of sine is cosine, but we don't know what the derivative of 2 to the power is. So let's jump back a slide and see if we can figure out, or let's just do it off to the side over here. Okay. 2 to the power, we figured out that 2 to the x was the same thing as e to the natural log 2 times x, right? So if we want to do the derivative of 2 to the power, we can treat that as these two arrows, which is a natural log of 2. Okay, so the first thing we do is multiply by the natural log of 2, and then we do e to the power. So these two arrows together are the same thing as the one arrow for 2 to the power. And this is natural log of 2 times, well, that's just linear with a slope of natural log 2, so its derivative is just natural log 2. And then this is natural log of 2 times x, and the derivative is e to the power, and so that gets the natural log of 2 times x there. So it's these two things multiplied together, but e to the natural log 2 to the x is just the same thing as 2 to the x. So the derivative of 2 to the power is natural log 2 times 2 to the power. We said the derivative of an exponential would always involve that same exponential. So if you want to leave it in terms of e's, you can do that. Or this is not a difficult thing to memorize as the derivative. And we'll write down what that looks like as an arrow diagram here in a second. And so if I pull things out, I've got a 10 times the natural log 2, those are the constants, times the 2 to the x, times the cosine x. And this would be the derivative of 10 times 2 to the sine x power. Again, pausing every once in a while to contemplate the fact that I can do, how quickly we can come up with these derivatives of functions that just looking at, we probably have no idea what in the world the function would look like. But we can come up with an equation that will tell us what the slopes of all the tangent lines on that function are, and it doesn't take us long to do it. Okay? We got less than 2 minutes to go here. I'm going to throw this on here, that if the function, if it's an exponential function with a base of b, then its derivative is going to be the natural log of b times b to the power. Okay? All it takes, in essence, to make these, the e to the x happens to be the perfect balance in there, that it lines up right on top of itself. As it gets away from e to the x, then it starts to change a little bit, but the change is just a vertical stretch. And that's what we see with the natural log of b. Natural log of b multiplied out in front is going to accomplish a vertical stretch. And so we just need to vertical stretch that original function to get it to go to the right place on the derivative. All right, I have 1 minute to go, and definitely not everything that we need here. So I'm going to stop at this point. I would answer any questions that you might happen to have right now.